Hello everyone. So I'm going to present a way to fix a well-known weakness of the mean field inference method for approximating multimodal posteriors. Mean fields is a variational inference technique used to solve large conditional random fields. Its usual applications in our field range from semantic segmentation to multi-camera people detection. Mean field is used to approximate an intractable posterior distribution P by a simpler one Q. The posterior is usually defined through a conditional random field. The closeness of the approximation is measured through the KL-Divergence, and the inference algorithm is used to minimize it with respect to the approximation Q. For mean field inference, we look for an approximation in the form of a fully factorized distribution. This approximation lets us perform inference even for very large models. However, it's sometimes too simplistic because it fails to model multimodal posteriors. To see this, we designed a simple toy experiment. Let us consider a binary grid conditional random field. Its unary potentials are drawn uniformly between 0 and 1, and it has strong attractive potentials. Because of the attractive potential, this model defines a posterior with two main modes, the 0 and the 1, 1, as can be seen by sampling. Mean field inference will correctly model only a single mode and completely ignore the other. Depending on initialization, it can be either the 0 mode or the 1 mode. The goal of multimodal mean field is to actually recover both modes, and therefore correctly model the multimodal posterior. Okay, more formally, we replace the fully factorized approximation used in mean field by a weighted sum of such distributions. Each term of the sum is called a mode, and we are computing each mode by solving a constrained mean field problem. Our goal is then to minimize the KL-Divergence with the true posterior, as in the naive mean field case. The underlying idea is that each mode of multimodal mean field will approximate the posterior correctly on a specific region of the variable state space. These regions are created via clamping, which means forcing variables to take specific values. The idea of clamping had been introduced before us. However, it was only practical for small conditional random fields of less than 100 variables. In order to apply our method to larger problems, such as the one envisioned, we had to introduce a technique called Cardinality-Based clamping, which lets us act on large groups of variables. In order to choose which variables to clamp, or in other terms, to decide on which parts of the CRF we need to add multimodality, we use a criterion based on phase transitions in the sense of statistical physics. Thanks to this method, we can find parts of the CRF which need clamping. As you can see in the image below, our method is able to find zones of uncertain labeling where we can then act. So for a given image, our algorithm produces multiple possible segmentations, such as the two ones that you can see here on the image that correspond to separate mean field modes. Then, in the case of video segmentation, the best sequence of mode can be recovered using temporal consistency. Likewise, in the case of multi-camera people detection, our algorithm produces multiple possible probabilistic occupancy maps, each one corresponding to a single mode. This is shown to achieve better tracking results. Thank you for listening to my presentation, and please come to visit us during the poster session.